Hello children, welcome to Yamuna's physics classes. Today we have to discuss the section 4.8 solenoid, and it is the main application of Ampere's circuit law. Now the question is, why you learn solenoid? For that we have to go back to a topic known as magnetic field of a circular loop. And you know that in that video it is specifically mentioned the magnetic field of the circular loop has a value mu0 Nia square divided by 2 into a square plus x square raised to 3 by 2. And the maximum value when x equal to 0, that is at the center. But when it goes on increasing x, not a, x means the distance, you can see that the curve is coming down, means the value of b is reducing. Or from center to the extremes, the magnetic field of a circular loop will be varying. So the magnetic field well inside the loop is variable or non-uniform magnetic field. But if the same loop, if you could take a number of loops and place in the form of an helix or a spring, simply spring, it will be a solenoid, and we can have uniform magnetic field within the solenoid. Inside the solenoid, you can have a uniform magnetic field. That is why you use a solenoid. So what is a solenoid? Solenoid consists of an insulating long wire. Each wire, I told you it is in the form of a helix or a spring. So each wire is insulated from the neighbor. Insulating long wire closely wound in the form of a helix or spring. Usual spring which you put inside the pen and all, you have the spring, the same spring. Its length is large compared to the diameter. Now, these three figures are explicitly the figures of NCERT text, and all the three are actually saying the same concept, but it is drawn in three different manner. But every figure, this figure have the common meaning. Okay, so let us proceed. We will explain each and every figure. Coming to the first figure, this is a simple structure of a solenoid. In this solenoid, you can see current is entering through this side and leaving through this side. So if I am looking from this side, so for example, if I have a ring like this or a singular loop like this, if you have a single loop like this, and you look at this from this side, I am watching from this side, so I can see the current is going and coming like this. Similarly, the same thing happens for each helix at the back. So the same thing is repeating for all the rings behind it. So it becomes a solenoid. So once again, current is going like this, coming like this, again like this, like this. Means at the top of this loop, current has a direction. Current has a direction out of the board. In this board, you have two perpendicular, either out of the board or into the plane of the board. So here the current is coming out of the plane of the board. And below at the bottom, you can see the current is going well into the plane of the board. So the 2 points here, this dot shows it is coming out. This cross shows the current is going well into the plane of the board. Now, the same figure is drawn with a cross section. This loop is cut in such a manner which is parallel to the plane of the board. So you can have two semicircles, one this side, the other one at the back of the board. So if you cut it into two, you can see that at this point and this point it has an opening. So at this point, upper point, current is out of the plane of the board. Lower point, current is well into the plane of the board. Okay, and now I told you, instead of a circular loop, if you have a solenoid, you can have a uniform magnetic field well inside the solenoid. So the question again, is there no magnetic field outside the solenoid? That's a question. So we will answer two questions. What is the value of magnetic field if it is there uniform inside? And is there no magnetic field outside the solenoid? So we will answer these questions one by one. Number one, we are going to do, we have to prove that outside this we don't have a magnetic field. Why? The answer is very simple. The same figure redrawn. The magenta dots at the top, yellow cross at the bottom. Redrawn. You can see dot at the top, cross at the bottom. Now, for each dot, you take the right hand grip rule to show the direction of the magnetic field. Hold the right hand with thumb pointing the direction of the current. So I am pointing thumb in the direction of the current. You can see the thumb is pointing in the direction of the current, out. So what about my curled fingers? Anti-clockwise direction. So anti-clockwise direction shows the magnetic field here. So each and every point, magnetic field anti-clockwise. Magnetic field anti-clockwise. So that particular figure is drawn here. So the white circles for each magenta dot shows anti-clockwise direction for the magnetic field. Similarly, bottom. At the bottom, what about the magnetic field? Sorry, what about the direction of the current? Into the plane of the board. Current is well into the plane of the board. So look at my curled fingers clockwise. The loop is going clockwise, clockwise, clockwise. So at this point, clockwise, again this point clockwise, each point shows clockwise magnetic field. So at the top you can see anti-clockwise loop, at the bottom you can see clockwise loop. One more thing, for each circles the tangent shows the direction of the magnetic field. So the blue circles, look at the blue circles. The blue circle shows that direction of the magnetic field is opposite to each other. Means tangents will be directed opposite to each other. So opposite tangent means what? They cancel each other. Therefore, over the solenoid, the upper portion and the lower portion, or means outside the solenoid, you can see the magnetic fields are nullified or cancelled. So there will be only negligible amount of magnetic field on the upper and the lower or around the solenoid. On the periphery of the solenoid, you have only negligible amount of magnetic field. Clear? Now the question is, what about the magnetic field well inside? It is uniform. For that, we apply Ampere's circuit law. So the same figure redrawn here. Same figure. This is magenta dots, this is yellow cross. The same magenta dots, the same yellow cross. Magenta dots showing current out. Yellow cross showing current in. In between you have uniform magnetic field. And again for the loop rule, you have two rules for the right hand. One for the straight conductor, the other for the circular coil. If it is circular coil, this is current, this is magnetic field. So look at this. This is my current. Look at the current. Current here coming out. Here going in. So this point refers to the top. This point refers to the bottom. Here you can see current is coming out. Dots. Here you can see current is going well inside into the plane of the board. So what about the magnetic field? Along the thumb, it is towards right. Therefore, you have a magnetic field towards right, uniformly well inside the solenoid. Now, we are going to apply Amperean loop. We construct an Amperean loop of rectangular shape. P, Q, R, S, P. and apply the law and find out what is the value of B. For that, the whole integral B dot dl PQRS loop. Cut it into PQ, QR, RS, SP, meaning PQ, QR, RS, SP, and find the values of B, dl and cos theta for all the four sides. Considering the first part PQ, you know B towards right and the direction of dl also towards right. Each element in this portion is known as a dl, but dl has the same direction as that of B. So theta comes to 0. But in this direction what will happen? B is towards right and dl perpendicularly up. So what is the angle? 90. What about the other side, RS? We have discussed already. The outer portions have zero magnetic field. So you need not think about dl and cos theta. B itself is 0 for this portion. And finally, what about SP, this portion? What about this portion SP? Again the same problem. You have perpendicular dl, B in this direction. So theta becomes 90. Now put the values, what you will get? This goes to 0, this goes to 0, this goes to 0. The remaining term is only PQ region. PQ region, you have small elements dl, integrate them, the total length will be L. Because it's a rectangular loop, this and this will be the same. So what is the total length? dl. But we know closed integral B dot dl is nothing but mu 0 times sigma I. Sigma I means what? Total current. Total current means what? Each loop carries a current I. How many loops are there? If n is the number of turns per unit length, inside L turn, how much? 1, 2, 3, 4, 5, 6, 7. You have to count. How many? That is n into L. So much currents. So sigma I is the total current in the loop. In the loop you have a total current NL into I. L and L cancels. The answer is B is equal to mu 0 times Ni. From this it is very clear. It is air core or vacuum. Next, N, the number of turns. As you raise the number of turns or the number of turns you are increasing and increasing, you can see B goes on increasing. I told you, for a single circular loop, it is non-uniform. But when it comes to a long number of loops, for a helix, the magnetic field goes to be uniform. So N, it should be long and long, so that field will be uniform. Also I, if you increase the current, what happens? Magnetic field around it also increases. So we have discussed three things. What is a solenoid? Outside you don't have any magnetic field. Inside you have a magnetic field whose value is mu 0 Ni. And we have used Ampere's circular law to find out the magnetic field. Hope it is clear. If you have any doubts, please put in the comment box. If it is okay for you, share and subscribe. And the channel link is there in the description. You can have playlists for the other lessons as well. Okay, thank you for listening.